Chapter 4 is about the chemical study of the chemical reaction. We do have a sample chemical reaction, and also it's going to talk about generally the concerns about the chemical reactions. We are talking about the energy required for chemical reactions, and then what makes a reaction to go fast or slow, and is like an introduction in general for any organic reaction. The examples that we are using to begin with this chapter is chlorination of the methane. So when we say methane with the 1 carbon and 4 hydrogen already, say chlorination is basically replacing one of the hydrogens from methane with chlorine. So the requirement is either heat or light. The product for monochlorination, and that means only one hydrogen would be replaced by chlorine, is going to be chloromethane, and the byproduct is HCl. So in a chemical reaction, old bonds are broken. These 2 bonds are broken. New bonds is forming. This is the new bond that is forming. So it's new bond is forming, and we have old bonds that are broken. When bonds are broken, energy is needed, and that energy is called bond dissociation energy. When bonds are forming, we have bond formation energy. Energy is going to be released. So if the reaction releases more energy than what is being consumed to break the old bonds, that reaction is going to be exothermic reaction. The excess amount, some of the energy is going to be consumed to break the old bonds, and the rest of the energy is going to be released to environment. Then you have an exothermic type reaction. So if your reactants start with this level of the energy, and then the products is going to go down, this amount of energy that is going to be released basically is the difference in the energy of the reactants and products. Is going to give you exothermic reaction. So if you have the energy diagram, you can say this is exothermic reaction because your reactants have more energy than the products, and the difference in energy, which is a delta H, has been released to environment. The other way to predict or to determine if the reaction is exothermic or endothermic is if you have the bond energy for the old bonds that are going to break and the new bonds that are forming. If the new bonds that are forming, the amount of energy is greater, then the difference is going to be released to environment. So you have 2 ways to determine that. Either the energy diagram is given, or the energy for individual bonds, the new bonds that are forming and old bonds that are broken, it will be given to you. So we talked about monochlorination, and that was just 1 chlorine replacing a hydrogen. If you don't stop this reaction, or if you don't set the condition for this reaction to only give you monochlorination, that's basically you limit the amount of the chlorine, you put lots of methane, the reaction would stop here. And if you don't stop, this reaction is going to continue. And as it continues, it's going to give you dichlorinated product, trichlorinated, and tetrachloromethane, or carbon tetrachloride. That's, you have CCl4, carbon tetrachloride, and you have methylene chloride here, CH2Cl2. So you have the 4 different product, or possibility of 4 different products. In order to get this product, you have to use a lot of Cl2 and limited amount of methane. That way you get all 4 hydrogen replaced by chlorine. In order to get monochlorination, you have to limit the amount of the chlorine and use lots of methane. It is sometimes hard to avoid presence of the other 2, but then you have to have like steps for purification. because these compounds, they are different compounds. One has 1 chlorine, 2 chlorine, 4 chlorine is obvious, but at the same time, they will have different physical properties, different boiling point. So if they have different boiling point, they can be separated by distillation. So after the product is formed, if you predict or you suspect that there are more than one type of product, you have to purify it. A mixture of 2 or 3 products is not valid, is not good. A mixture is not going to be very useful. You have to then purify. Now, so this reaction is a substitution reaction. That's what we are going to just classify as a substitution reaction. We do have a product and we have a byproduct. Okay, I don't have anybody in the waiting room. I don't have anybody in the waiting room, so I think Aaron is in different room. So please ask student to come in to the room that is probably hosted by me. That would be the solution. I'm sorry about it, but I don't have control of the other room. Thank you for helping. Okay, so when you study the reaction, you want to know about the reactants. What are the 2 reactants? In this case, methane and chlorine. What are the products? What is the byproduct? In organic chemistry, we are concerned about the organic product. Anything inorganic, we call it like byproduct. We want to know what is the requirement, like you need a catalyst, and that would be heat or light. And we want to know the mechanism for reaction. What is the mechanism of reaction would be a study of reaction step by step. What is happening first and what's happening on the next step. In this reaction, the mechanism of the reaction is known as the free radical chain reaction. There are few steps. You have initiation step, you have propagation step, and then you have termination step. In the initiation step, the starting material, which is chlorine, is going to dissociate when you shine light or apply heat to chlorine. Hemolytic cleavage of chlorine gas is going to give you 2 chlorine free radical, and that is the 2 free radical. Okay, that is given. You start with no free radical. That's how you recognize an initiation step. You have 2 free radical, and then you are going to end up with 2 free radical. You start with no free radical. That's initiation, starting the reaction. So no free radical, end up with 2 free radical.
Would you be able to tell with the photon there too?
The photon as a starting material, so the photon, it's possible that you would need heat or light for other steps of the reaction as well, but the indication based on classification or difference between the initiation, propagation, and termination, if you're specifically for free radical chain reaction, would be you start with no free radical and you end up with more free radical. So that's a starting reaction. For the chain reaction, you need the free radical.
So it's basically the splitting of the 2 chlorines into single ones.
Yes, to generate the free radicals to start the reaction. Okay. So what is free radical? Free radical is the atom with which is not satisfied with the octet rule, and it doesn't have 8 valence electron. So it's going to be very reactive. It likes to attack something. It wants to absorb an electron. It wants to gain 1 electron in order to be stable. So if you have bromine with 7 valence electron only, that is a bromine free radical, chlorine free radical, or hydroxide when you have 1 free free electron or unpaired electron, that is known as the free radical. What is unique about free radical, they are very reactive, and they are going to move to the next step of the reaction very easily. So the next step of the reaction is probably going to be faster because you generate very reactive species here. Like this chlorine Cl2 is not very reactive, and you have to use photon or heat. But when you come to the chlorine free radical, if it's in the reactant side, is going to start the reaction on its own to move to the next step. So on the propagation step, what happens in propagation step? In propagation step, just the reason I say this, it may not be in the books, but it's going to make it easier for you to recognize. One free radical is consumed, another free radical is produced. That's a propagation step. Okay. One free radical is consumed. This is a second propagation step. Free radical is consumed, free radical is produced. And you also have a product that is forming. So these two steps are known as propagation step. They are kind of promoting each other. Like the second reaction is going to produce Cl minus, the Cl free radical, chlorine radical is going to attack the methane. Then you get methyl free radical. Methyl free radical is going to attack chlorine. It gives you product, and then the chlorine free radical. So these two is going to repeat each other, and is going to be like linked to one another. One goes brings the other one, and then just repeats itself. It is like they are attached like the link of a chain. That's why it's called a chain reaction, free radical chain reaction. So it's going back and forth. And every time this cycle takes place, you have one molecule of the product that is forming. This reaction, or this step of the reaction, propagation step, is going to repeat itself 100 times before the reaction stops. So it's called propagation step. You have first propagation step and a second propagation step, and you have your initiation step. Now, the last step that we need to discuss is called termination step. And how would you recognize there is a termination step? Is like, if you follow the same trend, like for initiation, you have no free radical, and then you end up with two free radical. For propagation, you get one free radical consumed, one free radical produced, and you have two steps for propagation. When it comes to termination step, you start with two free radical, and you end up no free radical. Okay, that would be termination step. Examples of termination step: a methyl free radical with chlorine free radical would give you product. If chlorine free radical finds another chlorine free radical, it's going to give you Cl2. It's termination. It's classified as termination step because it does not produce any free radical. And then methyl free radical with another free radical can give you a byproduct of ethane, but this is not part of the propagation. It kind of breaks the link. Now, sometimes they want to stop the reaction, so they bring like inhibitors. At the end, let's say, is a time limit. When you have that time of the reaction, reaches that time of the reaction, then they add like inhibitors to stop the reaction, so they can, they can bring the inhibitors. But the other examples, which is not very, it doesn't follow the definition and is not very popular, you could say that if methyl free radical is going to collide with the wall, and it attaches to the wall, as long as it doesn't produce another free radical, it is classified as termination step. So you have less reactive steps. It's going to produce stable product that is just saying, that's it, stop here, no more reaction. So when you want to study the mechanism for reaction, let me just go to the one more time. You want to know that for chlorination, the type of reaction is a free radical chain reaction. And there are three major steps. You have initiation step, you have propagation step, and you have termination step. The propagation step, it kind of repeats itself multiple times, and it goes back and forth to generate to promote continues the chain, basically. That's why it's called the chain reaction. And termination step is going to produce less reactive product, and it will stop the reaction. It's end of the reaction. And about that point, you already have your product that you needed. What else you want to know about a chemical reaction? These are the review from general chemistry. I'm not going to put too much time on it because it's a review from the general chemistry, and you know it, and we don't use it too often, but I just want to make sure that you understand and just remind you or review that delta G, when it's a negative, that means the reaction is spontaneous. For delta G positive is a non-spontaneous. And that's the free energy, basically, is the free energy for the reaction. When it's negative, it makes the reaction spontaneous. For non-spontaneous, you have positive. What is K equilibrium? K equilibrium, it's for reaction that does reach equilibrium. And K equilibrium is defined as a concentration of product over concentration of reactant raised to the power of the coefficient. And that value for a given temperature is a constant number. The higher this value, that means the reaction is fast. The lower this value, or if you get negative exponents for the number, that means the reaction is slow. And we will see some of these example and in the next slide with the table with the different values. Delta G of a reaction is temperature dependent, and also the K equilibrium also, it can depend on the temperature. So at different temperature, the value can change. Okay. The relationship between delta G, which is the free energy, enthalpy, this is just purely how much it depends on the bond energy between reactant and product, how much energy is going to be involved in a reaction. And delta S is entropy. For a chemical reaction, you studied this in 1046, when you calculate or when you find out the value for delta G, delta H, and delta S, they are known as the thermodynamic values, and you have the values for the reaction. If delta S positive, that means that the reaction is going toward more disorder. If delta H is positive, that means is the enthalpy of the reaction is positive. That means is an endothermic reaction. Delta H negative, that means is exothermic reaction. Exothermic, endothermic is determined by delta H value, but spontaneity, it's determined by delta G. A positive value for delta G, that means that at the given temperature or condition, this reaction is not spontaneous. If it's a negative sign, it means the reaction is spontaneous and it will happen on its own.
And Professor?
Yes.
If delta G is 0, that means it's at equilibrium, correct?
If delta G is 0, that means at equilibrium. Very good. Yes.
Okay. All right.
Yes. Okay. Other terms that we want to study here is, like we talked about, hemolytic cleavage. When we say hemolytic cleavage, that means if you have a Cl with another Cl sharing electron, that's like when you have a Cl diatomic molecule that you have, if you spend some energy, which is the bond dissociation energy, is going to break evenly and hemolytic. That means that each one would take their share of electron and leave, and that is going to create like two free radical. That's hemolytic cleavage. When this happens, when you have the right amount of energy, and at the same time, the difference in electronegativity allows that is not much, and it does allow that hemolytic cleavage. If you have two species with greater or more significant difference in electronegativity, or one is like more stable with taking electron with, and the other one is more stable with not having the electrons, in that case, you have heterolytic cleavage. In a heterolytic cleavage, pair of electrons, pair of the shared electrons is going to go with one, and then no electron for the other. The piece that doesn't take electron would gain positive charge. The piece that is taking both of the shared electron would gain a negative charge. So when we learn about this in chapter 6 about the leaving group, when you have alkyl halide and you talk about the leaving group, like Cl, when Cl leaves, is going to take electron, and the cleavage at that point is going to be heterolytic cleavage. So basically, heterolytic cleavage is going to create ions. The delta H value for different bonds, it's different, but it's the same for formation and dissociation. But when you are trying to do dissociation, the delta H sign is going to be positive. If it's negative, that means the two chlorine, they bond together, they create the Cl-Cl bond, and then you get that energy back is going to be negative. So when bond forms, energy is released, but energy is released when the bond forms, and then when bonds are broken, energy is consumed. If you look at the total amount of energy, this is referring to the same reactions that you had as a CH4 plus Cl2 that yields CH3Cl plus HCl. In this reaction, when you have total amount of energy being released is greater than the total amount of energy needed, this overall reaction is going to be exothermic reaction. How much heat is going to be released to the environment is going to be the total of the two. So minus 782 plus 677, whatever the difference is going to be the delta H for reaction. Okay. Delta H for reaction is the delta H formation for the bonds that are forming, minus the total of delta H of bond dissociation. So heat needed, heat released. The difference is going to be overall heat for the reaction. And that is known as the delta H of the reaction. Yes, your question.
For bond dissociation, it's more stable because there's less energy, correct? Than if heat's being released when bonds are formed, it's less stable.
Exactly. Let's say you have chlorine free radical, it's going to be very unstable because it's not octet satisfied. When it does form Cl2, is going to become more stable, and the difference in the energy is going to be released. Now, if you have the Cl2 and you're trying to shake it back to the 2Cl, you have to spend that energy. Exactly. Very good.
Yeah. Okay, cool.
So that's the amount of the energy for delta H for chlorination or monochlorination of methane. So you learn basically all these, like in whole semester, about kinetic, about thermodynamics. So the values that we were talking so far, delta H, delta S, delta G, that was thermodynamic values. Then you learned also about the kinetic of the reaction. Kinetic of the reaction, when you have basically studies how fast the reaction will take place, which brings the rate law. So you have the rate law for a reaction, which is expressed based on reactants only, okay? K equilibrium is expressed based on products over the reactant, but when you're talking about the rate law is only based on the reactant. So you have the rate constant, concentration of reactant 1 to X, concentration of the reactant, second reactant to the power of Y. These values for X and Y is determined experimentally only. So for that, we have to do set of 3 or 4 reactions, keep concentration of the B constant, and then find the rate, change the concentration of A, find the rate. You see, like if you double the concentration of A, where concentration of B is constant and the rate is doubled, that is like a 1-to-1 ratio, that's going to give the value for X equal 1. If you double it, if you double the concentration of A and the rate it's quadruple, that gives you the value for X2. So this is like hypothetical question. You do need set of experiments in order to see which one is constant, what's the change of the concentration in A, and how does it affect the change in the rate of the reaction. But these numbers are experimentally determined. When you have those numbers, we look for the definition and we say that A is the order of the reaction with respect to compound A. Lowercase b is the order of the reaction with respect to reactant B. And overall is going to be A plus B. So we have the overall order as well. So again, a very quick and fast review of the rate law and the kinetic from general chemistry. So if you look at the Arrhenius equation, if you just use the application, a rate of a reaction, it depends on temperature, it depends on activation energy. So when you talk about rate of a reaction, how could you increase the rate of the reaction? You can look at some of these factors. The smaller the activation energy is, the faster the reaction. So if you have 2 reactions and then you have one with higher activation energy and the other one with the lower activation energy, the one with the lower activation energy is going to be faster. So the blue color is going to go faster than the red one. This is the transition state. That's the transition state. So the difference between energy of the reactant to transition state, that's the activation energy. The difference between energy of the reactant and product, that is the delta H value. So we have the delta H value, and then we have the activation energy based on the energy diagram. But if you look at this energy diagram, could say the smaller the activation energy, the faster the reaction. And that's what this equation also it provides. The greater the temperature, the higher the temperature, the faster the reaction. Obviously, if you increase the temperature, then you have more of the reactants that they are going to collide, and they meet the minimum amount of the energy, which is the activation energy, to go to the product. If you look at this diagram, I just want to make sure that you can read the diagram. Okay, so if the activation energy is very high, that's in the red zone, you only have the red shade number of particles, or that percentage, that can go through the activation energy and would go to the products. Okay, so you have different temperature also. So if you have the energy at lower temperature, the blue shade. At higher temperature, you get this light green color. So you basically have the whole thing here that is going to go to the product. That's under smaller activation energy. So you have the smaller activation energy. Even you have high temperature, if you have very high activation energy, you only get this much, which is the red zone of the molecule that is going to go to the product. So both of the factors is going to affect the rate of the reaction, activation and temperature. In general, the higher the temperature, the faster the reaction. And always the smaller the value for activation energy, the faster the reaction. And how does these shaded area translate to faster reaction? Means that how fast a product can form, how fast the change in concentration for product is going to take place. So if you have greater shaded area, or the area under the graph that is shaded, that means more molecules are going to product, and that translates to faster reaction. So those are the major factors that affects the rate of reaction. First of all, you have to have the rate law, the effect of the concentration. The other factors are temperature and the activation energy. Based on mechanism of the reaction, if you have like one-step reaction or two-step reaction, is going to also be another factor, which we are going to just mention about this in this chapter and learn more in depth in chapter 6. So if you have two-step reaction, I think we have the diagram, and the diagram is going to be more pretty than this one. So when you have like intermediate, that is a free radical is forming, let's say here, free radical is forming, you have two-step reaction. You see, you have two activation energy. This is activation energy 1, and this is activation energy EA2. So you have a slow step. This side of the molecule, the part of the reaction is slow, and the second step is going to be fast, because activation energy is smaller for second step. It's going to be fast. What is going to inhibit the reaction is the slow reaction. Let's say if you have two exams, one is like very hard exam and the other one is an easy exam. How many people is going to pass the class if you had only two exams and one was very hard and the other one was like very easy? Is like, it depends on how many people pass the hard exam, right? Because anybody who passed the hard exam, there's a very good chance that they will pass the easy exam. So it's the same idea here. When you have two activation energy, that means your reaction is two-step reaction. The slow step is going to determine the rate of the reaction. That means only chemicals that are involved in the slow step of the reaction is going to affect the rate of the reaction. It, regardless of how much you have the other compound, is not going to affect the rate of the reaction. So we know from this slide that temperature is going to affect the rate of the reaction, and the activation energy is going to affect the rate of the reaction. As I promised, I have a better picture here. Someone else draw this picture. We have activation energy, the difference between energy of reactant and the transition state. What is transition state? Is like it looks like a 2+, but it's basically one vertical line and two horizontal line. So the transition state, meaning that is the highest point of the curve in the energy diagram. That means the most unstable situation for the molecule that is going through and is changing to the product. So it has to pass that it's like students the day before final exam, or if you're giving like an entrance exam like the day before. Very high energy, and high energy means lower stability. So that's the time that you're not the more relaxed. Relaxed meaning you have less energy and you're stable.
Professor.
Yes.
It's high energy because that's where the bonds begin to break before other bonds can form, right?
Exactly.
Okay.
Yes,
right.
Because especially if you are dealing with carbon is tetravalent and wants to have the 4 bonds, doesn't want to lose one, doesn't want to gain one. Sometimes you get a situation that one bond is breaking, the other bond is forming, and you have three other bonds, you make the molecule of carbon going through like this disaster. Doesn't like that. So it's going to show like very high energy. Another time you have one of the hydrogen is leaving and the carbon doesn't want to lose that. Then you have, depends on the mechanism, you could have this as a transition or this one as a transition. In two-step reaction, this is a transition. So for two-step reaction, we one-step reaction, this one is a transition. So you have the carbon is losing its stability. This is the point that yes, is going to lose that stability. Yes, you're right. Is affecting the stability of the molecule. Okay. Two-step reaction. In a two-step reaction, we talked about two activation energy, and the one with higher activation energy is going to determine the rate of the reaction. So in this example, because it specifies for free radical chain reaction, if free radical forms faster, the reaction is going to be faster. And what makes this free radical to form faster is that the free radical that is forming is going to be a stable free radical. So it's not going to be very unstable, very reactive. If it's stable, it's going to form faster. There are two facts that you have to know by heart. If you have low activation energy, it's going to happen fast. That step of the reaction is going to happen fast. The slow step is going to be high activation energy. Now, the more stable the intermediate is, the faster the reaction is going to be. That's another factor. So when we look at other intermediates and we compare it, you could see that if you have more stable intermediate, it's going to form fast.
Can you repeat those two one more time, please?
Okay, one, if you have two-step reaction, multi-step reactions, so you could have three-step reaction. In multi-step reaction, the step with the highest activation energy, which is also the slow step, is going to determine the rate of the reaction. So the lower the activation energy, the faster the step. That's one. Second, when there is intermediate involved or the intermediate forms in a chemical reaction, the more stable the intermediate is, the faster it's going to form. So basically, it lowers the activation energy. The more stable it is, the faster it's going to form.
Professor, how can we tell if it's stable or not, or if one's more stable than the other?
Okay, that is a very good question. I can answer that right here, or I was going to wait for later. Let's say if you have a methyl free radical, and then you have a propyl free radical. Okay, carbon is electron deficient. It needs electron. There is no group that can give electron to methyl, so it's going to be very unstable. But when you come to propyl free radical, you have these two groups here, and both of them are electron donor.
Bonded. Okay.
By experience, it shows that the alkyl groups, they can donate electron. So it stabilizes this free radical that is basically a secondary free radical. That means this carbon is attached to two other carbon. Now,
So in a sense, if it's a longer chain, it becomes kind of more stable.
The number of groups is going to take the priority.
Yeah.
Okay. So if you have like one group that is supporting versus two groups that is supporting, so this is like a primary, and you have a secondary. And this is a methyl free radical. So if you had a tertiary, it would be more stable than secondary, more stable than primary, and more stable than methyl free radical.
I got it.
So that determines the stability for intermediate if you have free radical, which happens to be the same for carbocation. I think that's toward the end of this chapter.
So the more groups attached to the free radical, the more stable it is.
Exactly. Very good.
Gotcha.
Yes. Yes. And also the nature of the reactant. If you have chlorination, bromination, or iodination, It's going to make the reaction slow or fast as well. That this is the nature of the reactant. For iodine, the activation energy is very high and the reaction is going to be very slow. The rate of the reaction is to -19. And then for fluorine, because it's very reactive, the rate of the reaction at 27 degrees Celsius is going to be 140,000. That is the formula or the unit for rate is always mole, the change mole per second, change in concentration, right? Over the time. So if you increase the temperature, all of them is going to increase. But even at low temperature or at any given temperature, fluorine is most reactive of all other halogens, and iodine is the least reactive. So usually we don't deal with these two reactions. We only deal with the chlorination and for bromination. Chlorination is an exothermic reaction because this is the rate is over 1. And then bromination is a smaller value for the rate, and the is actually endothermic reaction, is a slower reaction. You see that at high temperature, it increases. The rate is going to increase at high temperature because temperature can affect the rate of the reaction, especially for endothermic reaction. If it's endothermic, if you increase the temperature, it's going to affect more significantly. So these are some of the conclusions of or statements that you could read from the table, but is also listed down. So for bromine to react, it must be heated up because it's an endothermic reaction. Okay. We have chlorination energy diagram. Again, activation energy, transition state, and then you have your product. Basically, this is formation of the methyl free radical, which is the first step of the reaction. So understanding the value for delta H is the difference between the value of the reactant, energy of the reactant, and the product or the intermediate in this case. And activation energy is the difference between the energy of the reactant and transition state. Okay, so we have the difference here. We get two products. Okay, if we chlorinate propane, there is a chance that a primary hydrogen or primary carbon would be chlorinated, or secondary carbon would be chlorinated. If you look at the value of 60% versus 40%, what does it say? It says that chlorination on a secondary carbon is faster than the primary. That's why you're getting higher percentage of the chlorination. More importantly, this is coming from chance of only 2 hydrogen. We have only 2 hydrogen in the secondary position, but we have 6 identical hydrogen in the primary position, and either one of them, each one of them can be chlorinated, and still we are only getting 40% of the product.
Professor?
So, yes.
How come we always include the other hydrogen on the other side? You label the first carbon, which is CH3, second carbon CH2, and then CH3. Why do we always add those CH3s together? Like, how come?
Okay, if they're identical, like this one is a primary carbon and this is also primary carbon, is attached to one another carbon, and so they are chemically similar. If they are chemically similar, they could both get through chemical reactions. Let's say if instead of taking this carbon and having chlorinated, so you take the other carbon and chlorinate it. And can you name this compound after I draw the structure. So if I say CH2Cl, what would be the name for this compound? It's going to be 1-chloropropane, right? So regardless, if you have this carbon being chlorinated or this carbon being chlorinated, the product is going to be 1-chloropropane.
Got it.
So basically, for a symmetrical molecule like this, these hydrogens are identical. That's why we are adding together.
Got it. That's why we have 6 hydrogens on the primary carbon.
Yes.
Okay. All right.
And then we have 2 hydrogen on the secondary
Yeah,
carbon.
secondary.
Only 2 hydrogen responsible for 60% and 6 hydrogen responsible for 40%. That says that a secondary chlorination is much faster. And why is faster? That goes back to the reason that I said, if you have a free radical that is a primary, in this case, CH2,
Hydrogen.
versus a secondary free radical,
ALS hydrogen, right?
secondary free radical. This is more stable. And because the free radical that is forming by losing secondary hydrogen is secondary free radical and is more stable than this primary. And the reason for secondary to be more stable is the number of groups that is attached to this free radical carbon. You only have 1 on this side. So that's why I say number of group attached, it takes priority over the size, because if you look at the size, you have 2 carbon, and then number of groups, you have like 2.
2. Yeah.
So the secondary is going to be more stable than the primary, and that's why higher percentage of secondary is forming. Because of the stability of the intermediate for secondary is greater compared to the primary.
Which is why it yields more product. Okay.
Yes. The more stable intermediate yields major product.
Yeah, and it'll be faster. I got it.
Yes. Okay, anyone with the questions? Anyone with the questions about the difference between a primary and secondary, or why we are getting higher percentage of the secondary? So this calculation here, it just shows if you consider the number of hydrogen that are primary 6 versus only 2 hydrogen that is secondary, that is going to even make the matter more significant, right? Because you get like 30% of the product per hydrogen for secondary, and you get like 66.67% per hydrogen of the primary. But I think most of you got it when I said six hydrogen only gives 40%, 2 hydrogen gives 60%. That says that a secondary free radical is a lot more stable. And then when you say secondary hydrogen, that means the carbon is attached to 2 other carbon that carries the hydrogen. If you have a tertiary hydrogen that is attached to tertiary carbon, and what is a tertiary carbon? That means it's attached to 3 other carbons. A primary carbon, that means is attached to only 1 other carbon. So when we talk about R, in general, is like an alkyl group. So the first thing that you have here is a carbon that is attached to this carbon in the center. So and since I promised that I will stop at one point and work on the group, let's just go to slide number 25 and stop, because I keep moving up to the next slide, and I don't want you to be worried about what I promised. Okay, so for halogenation or chlorination of the propane, as we saw earlier, we have 2 types of free radical that it's forming, because we have 2 types of hydrogen. We have primary hydrogens, primary hydrogen, and a secondary hydrogen. So we get only 2 different type of free radical or intermediate. And we saw that the more stable intermediate, which is the secondary, is going to yield to formation of the major product. So the energy diagram if you can read the diagram, that's like, it says a picture says 1,000 words. The stability of the intermediate for secondary carbocation has less energy, is more stable than the primary carbocation. And the more stable the intermediate, the faster the reaction. So you can just go to the stability of the intermediate based on the amount of energy each one has.
For the exam, are we mostly going to be dealing with these, the chlorination and bromination? Just the simple
No
propagation?
fluorine or iodine, just the chlorination and bromination as an example.
Okay.
Yes, and the understanding of the mechanism that you have the initiation step, you have the propagation step, you have the termination steps, and then also the difference in the percent of the product. What's the major product, what's the minor product, when there's a possibility for more than one product. Let's say if you do monochlorination of ethane, how many products would you get? Monochlorination, how many product can you get here?
One product?
Only one product, because it doesn't matter which hydrogen is replaced.
There's
With
only
the
one
fluorine,
radical.
there's only one name for it. Okay? And then for methane, the same thing. But when it comes to propane, then you have two types of hydrogen, so you get two products. If you have butane, you get two products. But if you have the product that you get like a tertiary. So this is like an isobutane. So you have one primary. That's the primary. I'm sorry, one tertiary, single tertiary, and all of these are primary, and primary. Okay, so when you remove this hydrogen, the amount of the energy that is consumed compared to you have the 381 delta H, you have 410 for primary, for secondary that decreases, and for the tertiary is much lower than either one of them. For methyl is the greatest. So when you have that delta H value, the higher the positive delta H value, that means that is more endothermic or requires more energy. And if anything requires more energy, it's going to be slow. If it requires less energy, that means it's going to happen fast. Because a tertiary free radical is more stable than the secondary, is more stable than primary, is more stable than methyl free radical. So stability of the intermediate, it's kind of the cause or the effect on the delta H value and how fast this reaction is going to take place. Okay. So which one is more reactive? A tertiary or primary?
Primary?
Primary.
Primary is going to be,
More.
I'm sorry, primary more reactive than the tertiary?
No,
The other way, right?
the other way. Tertiary is more reactive.
Tertiary is more reactive. Okay, tertiary is 5.5 times more reactive than the primary. So the amount of the product that you are going to get is going to be 5.5 times per hydrogen.
But didn't we say that the tertiary is gonna be more stable?
Yes,
Yeah.
Yeah, so it's less.
tertiary free radical is more stable. That means, let me bring the slide back. That means removing of the hydrogen is going to be easier. So tertiary free radical, okay, I'm glad you said it because I don't want you to mix these two. Tertiary free radical is more stable. That means removing of the hydrogen from tertiary carbon is easier and it takes less energy, requires less energy, so it's going to form faster. And if you had a choice between removing hydrogen from primary carbon or tertiary, the tertiary is going to be removed much faster, and tertiary would yield to major product.
Why
It's
is
removed.
that, Professor? Like, because if it's tertiary, wouldn't be having like a bigger electron cloud surrounding it or something?
That is a good question for a tertiary. So if you had one step reaction, that means that chlorine would have come in at the same time hydrogen was leaving, then you are right, because you have this big steric hindrance and they don't like it. But since hydrogen is going to leave, okay, hydrogen is going to leave, then chlorine comes in, then is not, and the step that hydrogen is leaving is the slow step of the reaction. So we only look at the slow step of the reaction or formation of the free radical. The next step is fast, so we don't have to worry about that in the process of determining the rate of the reaction.
So you will
If you
say,
had one step reaction, it would, your statement would have been correct. Yes.
okay, so you will say that since they're more stable,
Mhm.
they have less energy contained in the whole molecule. So that is what is so easy for them to break bonds with
Yes,
each other and being like,
be on it on their own. Like you know, if you have okay. So the energy diagram, we have two energy diagrams. We are dealing with bromination versus chlorination. The difference. Bromination is exothermic reaction. That means the delta H value is positive. So delta H is greater than 0. For chlorination is exothermic. So this is the endothermic. These are some observation. So when you read the graph, as I said, a picture like says 1,000 words, you have a lot of information that is here. So you want to look at all the information and be able to write the conclusion or statement, what is happening here. So chlorination is exothermic. Why is it exothermic? Because products, they are more stable than the reactants. Delta H value in this case is negative, is less than 0. The same thing. Exothermic and delta H less than 0 is the same thing. Both of them would give you two products, a 1-bromo or primary free radical and a secondary free radical for both of them. Okay. In this case, you have a primary and a secondary. So when the primary and secondary forms, it's regardless of it's coming from bromination or chlorination, primary and secondary, they are different. The difference in the stability is like 13 kilojoules. And this number and the diagram shows that secondary is 13 kilojoules more stable than the primary, or has that much less energy, and the lower the energy, more stable, more relaxed. Higher energy meaning less stable and is going to be more agitated, aggravated, anything that you want to call it. Not stable, very reactive. And the transition state even for the secondary is going to be lower than the primary, and the energy of the secondary free radical is lower than the primary. So these are some things that you have seen it before and you can predict, you can read it. Something new that I want to bring your attention to is like the transition state in chlorination is right here, very close to reactant, but transition state for bromination is very close to the product side. Okay, so this basically, in terms of the energy, the product is almost formed in the transition state. So the product is almost formed, but for chlorination, the product is all the way down here compared to the reactant, even though it's intermediate. So transition state is very close to the reactant. This happens for chlorination for being more reactive. So we call that chlorination to be like more reactive, but bromination is more selective. So it's more selective, and you actually get more secondary in bromination compared to the chlorination. Because bromination is very selective, and because it's more selective, it's going to select the most stable intermediate. But chlorination, because it's very reactive, it doesn't give chance to itself to go and search for which one is more reactive. Should I go to the most reactive? Should I go to less reactive? And it's going to go on, on its own. So I'm going to pause that to be understood. Okay, so for reactive bromination, because it's for selective reactant, the product and transition state, they are close in energy. For reactive, the transition state is close to the reactant, to the energy of the reactant, to the structure of the reactant as well. So for endothermic reaction, transition state is a product-like. Exothermic reaction, this is like a more reactive. Reactant. Transition state is reactant-like. And this was actually presented by Hammond. It's called like Hammond postulate. It was a postulate, or it was just an observation, closely monitoring the reaction mixture and see what is happening. For chlorination, transition state still very close to the reactant, but for bromination, transition state is almost like the product. Okay. To stop the reaction, we talked about the inhibitors. Inhibitors, that's like stopping the reaction. Something would be added to reaction mixture that is going to stop or change the free radical to less reactive or to a stable molecule, and then the reaction would stop. That's opposite to catalyst. So when you have catalyst, it would make the reaction to go faster. Inhibitors would make the reaction go slow. So you would see that the links of the chain will break or will stop at the end. That's the end of the reactions. That's like one step for like termination. So we talked about the stability of the free radical. Free radical tertiary is more stable than secondary, more stable than primary, more stable than methyl. Same thing for carbocation. For carbocation, tertiary is more stable than secondary, more stable than primary, and more stable than methyl. Okay, methyl carbocation. How do you justify it? Because this is electron deficient. It needs electron. What is our group doing here is giving electron. The other group is giving electron, and the third one is giving electron. If you have like 3 siblings who is willing to help you the time that you need support, you'll be better off than not having any support system. So you have like no support system for the methyl carbocation, but you have 3 support system for the tertiary carbocation. And these support system, they are there to stabilize it. So as a result, tertiary carbocation is more stable, and it goes down as the order goes down. For carbo anion, what is carbo anion? Carbo anion is carbon with a negative charge. It's going to be the opposite, because when you have too much electron on the carbon, doesn't need the electron support from the other group. So for carbo anion is going to be, so if you have like a CH3 with the negative charge, that is pair of unshared electron, and the the negative charge is going to be more stable than the primary, than the secondary, than the tertiary. The tertiary is going to be unstable because you have pair of unshared electron, you have the negative charge, and you have R groups that they are trying to give you, more electrons. Already has too many electrons, doesn't want to handle the negative charge, and you're bringing more electron is going to make it very hard for carbo anion. Carbo anions, if you have primary or metal, they are in better stability shape. So this stabilizing group or the support group that they are giving electron, they can be in through the inductive effect or the hyperconjugation. So basically overlap of the sigma bonds. But in general, if you know that R groups are support groups or they give electron or they are electron donor, that should be sufficient. So it can be hyperconjugation or it could be electron density through the sigma bond. It's just electrons are moving slightly over to the carbon with the positive charge. So we talked about the free radical, we talked about the carbocation, and then carbo anion as well. Carbo anions, they are destabilized by groups. If it's too hindered, doesn't like it at all. When you have an electron withdrawing group, is going to make the molecule like more acidic. So this hydrogen is going to be like more acidic because you have that many bromine attached to it. So hydroxide cannot remove hydrogen from methane, but since you have 3 bromine that is pulling electrons, it makes this molecule more acidic, is going to remove hydrogen from the group or from this molecule. Removing hydrogen requires a base, and if the hydrogen is not acidic, you cannot, regardless of what base you bring, is not going to remove the hydrogen. In order to remove the hydrogen, it must be acidic already. So it's a weak acid. That's why the sign for the equilibrium is shifts toward the more stable or weak acid. So you have a base here, is a strong base. This carbo anion is going to be very strong bases because it's coming from weak acid. The weaker the acid, the stronger the base. Acid-base conjugate, remember chapter 2, acid-base conjugate. If the weaker the acid is, the stronger the base. So this is like a very strong, carbo anion is a strong base. How do we know carbo anion is a strong base? Carbo anion can remove hydrogen from ammonia. Ammonia is basic. Is a weak base, but it's basic. So if carbo anion can remove hydrogen from basic compound like ammonia, that means it's a strong base. So that is the proof that this is a strong base. Okay, and this is the last slide of the chapter, which is summary of stability of intermediates. So we have carbocation, carbo free radical, carbo anion, and carbene. Carbene is not, you don't have primary, secondary, or tertiary. It's just the carbene that is missing 2 hydrogen, but at the same time has pair of unshared electron, is known as carbene. Okay,